Unit 8, Video 15. In this video we're going to introduce and just touch upon a very important concept in chemistry, the concept of equilibrium. We're going to apply it to acids, or introduce it in conjunction with acids, but it can actually be applied to many different types of reactions. Chemical equilibrium. The concept of equilibrium applies to a very big proportion of reactions and these reactions occur in both directions simultaneously, in the forward and the reverse direction. So we all are used to reactants forming products, but it turns out that products can actually form back into reactants. So the reverse process can happen. So this is a very simple reaction between N2O4, dinitrogen tetroxide, and it actually dissociates, or actually decomposes, not dissociates, decomposes into two NO2 molecules. And this happens naturally. So if you just create some N2O4, it naturally will decompose into NO2. But it turns out NO2 can actually get synthesized back into N2O4, and both processes happen simultaneously, and it depends on the temperature. So here we have a cold temperature. So if the temperature is, we'll say, 0 degrees Celsius, you actually get yourself N2O4, which is clear. If the temperature is, we'll say this is 80 degrees Celsius, you actually will get NO2, which is a brown gas. You can actually see this happening in both directions. So this is called an equilibrium reaction, where both the forward and the reverse reactions happen simultaneously. Now, to depict equilibrium, what we'll do is we'll use a double arrow. So in this case, we're using a double arrow. You can actually draw it like this as well. You'll see me draw it like this most of the time. Sometimes they'll draw a single arrow this way and a single arrow in the reverse direction. But since both reactions are occurring, what happens is you reach a state of equilibrium, and this equilibrium contains both reactants and products. Maybe more reactants and less products. So instead of having a reaction completely finish, producing all products and practically no reactions, that's kind of the standard way a reaction happens. In this case, you actually reach equilibrium where both the products and the reactants are still there, and they're still reacting essentially. And every reaction has what's called an equilibrium constant, a big K with an EQ down at the bottom, and it's set up to be products over reactants. It's actually products over reactants, and then to the power of their coefficients. So this 2 actually comes from the coefficient of the products. If there were coefficients in the reactants, there's a 1 essentially on the reactants. That goes up here to the first power. So essentially it's a ratio. The equilibrium constant is a ratio of products over reactants. So the magnitude, how big K is, for example, if K were 350, what this means is you have a lot of products because the number at the top is big, not a lot of reactants. And if the K is a small number, say if K were to be 0.035, the opposite is true. You have a lot of reactants, a big number on the bottom, not a lot of products. So the K, the equilibrium constant, actually tells you roughly what the situation is like at equilibrium. Now the way we're going to apply this to acids and bases is that weak acids and bases are actually equilibrium systems. So the weak acid, in this case HF is the weak acid, dissociates, breaks apart into hydrogen and fluorine, but it dissociates partially, which means it exists mostly as undissociated. So what happens is an equilibrium is set up to where most of the substance exists on the reactant side. A little bit of products are made, essentially. And you can think that every time the products are made, they go back to the reactants and make the reactants. Most of the products make the reactants. So in this case, and actually for all weak acids, the equilibrium constant is small, 6.6 times 10 to the negative 4. It's a pretty tiny number, meaning there's a small amount of products at equilibrium. And if there's a small amount of products, there's not much H+, so it's going to be weakly acidic. And here it says that all weak acids will have this small Ka. The KEQs, equilibrium constants, they actually designate them as Kas for the equilibrium constant of an acid. So Kas are specific for acids. So weak acids actually are equilibrium systems with small equilibrium constants. So we're actually we've developed a new definition for acids using equilibrium, and that's the Brønsted-Lowry acid. So Brønsted and Lowry were two chemists of yesteryear, from, looks like they're Danish. This looks like a letter from the Danish alphabet. And the acid was defined as a chemical that is a proton, or H+, donor. So proton just means hydrogen ion donor. So acids donate protons. Bases, on the other hand, are chemicals that are proton acceptors. So H+ acceptors. So acids donate H+, bases accept H+. So this is the new definition of an acid and a base in light of equilibrium, and we'll show you how this works. So here is what a Brønsted-Lowry acid would look like. Hydrogen, fluoride in this case, hydrofluoric acid, will dissociate, give off a hydrogen. So HF essentially gives off its hydrogen. So now F- is left behind. Oftentimes it's written because they have to give it to something. The H+ has to be given to another substance, and the other substance in this case is water, because acids create acidic solutions in water. So H+ is given to the water, so the H is given to here, and that's how you get good old hydronium, so hydronium ion. Now this is an equilibrium system, and so we have a double arrow, and essentially what we have is most of the reaction sits on the left still. Very little products are formed, and that's why it's a weak acid. You can do the same thing with weak bases. So NH3 is the famous weak base. Now, since bases are hydrogen acceptors, it has to accept the hydrogen from somewhere, and it actually accepts it from the water. The H+ is the one that actually gives it up. So once it accepts it, it becomes this substance. OH is left behind. And this is actually how ammonia, now you don't see an OH anywhere on ammonia, but it is a base. We know it's a base, and here's how it acts as a base. It actually creates OH indirectly by taking the hydrogen from water, leaving behind the OH. So that actually is how ammonia is defined as a base, and it's actually quite basic. It's a weak base, but it's medium weak, not strong, but not too weak either. All right, so now with looking at it through equilibrium, every acid has what's called a conjugate base partner, a conjugate base, and every base has a conjugate acid partner. And conjugate acids and bases will differ by one proton. So let me show you what this means. HF then has a partner, and that's F-, and it's simply taking the H out. If you remove the H, if it donates the H, it's left with F-. NH3's partner is actually NH4+. NH3 is a base, so it accepts an H+, becoming this. H2CO3's partner, this is carbonic acid's partner, is HCO3 with a minus charge. Again, he gave up one of the H's, or H+. Notice here, when you give up the H+, you end up with a minus charge because a positive ion was removed. So these are conjugates. And the way they connect together is that the acid, which is HF in this case, will donate a proton to water, which accepts it, so it becomes the base. Because remember, bases accept protons. So when that happens, F- results and H3O+ results. Now this is the reaction going in the forward direction. So going in the forward direction, H+ is given to water. HF gives an H+ to water. In the reverse direction, what happens is F-, if you look from the perspective of the products, F- is actually accepting an H+ from H3O. When that happens, you reform back the HF. So from this perspective, because bases accept hydrogen ions, F- is actually a base. And acids give up H3O+, hydronium ion, is actually an acid. This would be the reaction going in the reverse direction. And when we put the two together, what happens is we get this equilibrium system. This is the system that we saw earlier on. This is the equilibrium between HF and water. And the conjugates are here. So HF has a conjugate of F- because they differ by one hydrogen. So this is the acid, and this is the conjugate base. Same thing with water. Water is the base because it's accepting the H+, and its conjugate is hydronium ion, which is one hydrogen different from the water. So that is how this business of acid and conjugate base works. So here's what we can do: a few example problems. The first example problem asks, what's the conjugate base of H2SO4? Well, if this is a base, if H2SO4 is a base, then, rather it says what's the conjugate base of, apologize. So the conjugate base is what we need. So this guy's the acid, in other words. What's his conjugate base? That's the question. What's his conjugate base? So an acid, by definition, gives up an H+. So this guy will give up an H+, essentially, give away an H+. And what will result is HSO4, but because we removed a positive ion, we now have a -1 charge. This is actually bisulfate, or hydrogen sulfate ion. And this is the base. This is the conjugate base. This is the answer, in other words. If we ask the same thing, what is the conjugate acid of this substance? Well, if it has a conjugate acid partner, then he himself is actually a base. So its conjugate acid results when the base accepts an H+. So it'll actually accept an H+. And you can plot the H just together with these. Now you'll have 3 H's at the back. You get yourself CH3 NH4. NH3. So this would be a 3 with a +1 charge. You can leave it as a plus. So this is the conjugate acid of this substance. This substance is actually methylamine. It's called methylamine. And it sounds like ammonia. This is methylamine. And it sounds like ammonia. There's a lot of ammonia-based bases that are nitrogen-based, essentially, that kind of sound like ammonia. Alright? Now we can do the same thing, except we can write out the whole equation. Before we do that, this explains why baking soda, HCO3 with a minus charge, is a base. Now we showed you in class that it is a base. And if you put baking soda together with water, or with anything else, it'll be basic. And here's how we explain it. You take carbonic acid, and you react it with water, and then carbonic acid gives up the H+, since it's an acid. What results is this substance. Now this substance is actually a base, because going back the other way, the reaction shows him accepting an H+. So because he accepts an H+, he is a base. So that's why if you just take him and pull him out of a bottle, say in the form of sodium hydrogen carbonate, what happens is the sodium dissociates, falls off, it's just a spectator ion, and you result with this substance, and this substance reacts as a base, going in this direction, and actually makes the solution basic. Now in fact, HCO3 minus, a bicarbonate, is very special in that it can act both as an acid and a base. The reason it can go on and act as an acid is because it has one more ionizable hydrogen to give up. Carbonic acid is actually diprotic. So if you get to the middle of it, you can actually accept or give up a hydrogen. So it's amphiprotic. Amphoteric. Amphoteric. Amphiprotic is a little different. Amphoteric means you can act as an acid or a base. Water is the other famous amphoteric substance that can go become an acid or a base. And it's actually really important. These substances are real important because they serve an important purpose in creating what are called buffers. And this is a very famous buffer. Buffers keep the pH steady. You'll study them in another class, but buffers are very important to chemical systems, to keeping the pH stable. Alright, let's finish up with this one. Let's write the equation of H2PO4 minus acting as both an acid and a base. So we'll write it first as an acid. Now, H2PO4 is also amphoteric, and this is dihydrogen phosphate. And what we can write as an acid, we'll write H2PO4 minus, and we'll write it reacting with water. In our cases, we'll react this with water, unless it says otherwise. So we'll actually write a double arrow, because this will be an equilibrium system. Because H2PO4 is acting as an acid, it will give up an H+. So when it gives up its H+, when the H+ is given up, what will happen is it will become HPO4 with a -2 charge. You remove a positive, you get 2 negatives. And it gave it up to water, the H+ joined in with water, and water became hydronium, H3O+. And we know that hydronium results from acids. Anytime you form this substance, you have an acidic solution. Now this doesn't happen completely, it doesn't ionize completely, this is a weak acid. So if equilibrium were to set up, most of the equilibrium actually exists on the left side of the reaction. A little bit of it exists on the right. If you were to see a Ka for this, the Ka would be small, maybe 1.5 times 10 to the negative 8 or something like that. It's actually pretty small. base, we can write it also acting as a base. It's amphoteric. So as a base, H2PO4 minus 1 charge will also react with water. And as a base, bases by definition accept protons. So we're actually going to show it accepting an H+. And then once it accepts it, it becomes H3PO4. This is good old phosphoric acid. Notice no charge because the H+ canceled out the -1. What's left over then is, since it's accepted it, an OH-. So notice it's acting as a base. Bases essentially produce hydroxide ions, and that's what we're showing H2PO4 doing. Now, you can actually connect them. These two are conjugate partners, and these two are conjugate partners. And you can do the same thing with the top one. These two are conjugate partners, and so are these two. They're conjugate partners. Good. And to show you here, water, so this is the acid we said, we wrote it as an acid. Water is actually acting as a base in this reaction. Since it was acting as a base in this reaction, water is acting as an acid. So water as well can do both. Alright, so this wraps up the lesson. We'll do some calculations with these weak acids in the next lesson.